Welcome to the next chapter. It's energy changes in physical and chemical processes. Now, energy is the term we all come across each time and place where science is taught, and energy is simply the ability to do work. There are many forms of energy, which include heat energy, kinetic energy, electrical energy, chemical energy, and so on. Energy is measured in joules. But this offers no limitation to the usage of energy, because one form of energy can be transformed to another. But there is one more thing. You can never create nor destroy energy. Now, in essence, what that means is that the total amount of energy in the universe is constant and does not change. I know it is hard to imagine that. You see, there are forms of energy that are not useful in their state. Take, for example, a body at rest. The body possesses potential energy, but this energy does not do any work. So until the potential energy is converted to kinetic energy, that is energy in motion, only then can you see energy at work. Notice that in converting the potential energy to kinetic energy, no energy was created, neither was any destroyed. When you heat a substance, the heat absorbed by the molecules is converted to kinetic energy, which makes the particles and molecules to vibrate and move faster. The law of conservation of energy states that energy can neither be created nor destroyed. It can only be transformed from one form to another. Now, of all these types of energies, we shall be interested in heat energy. And heat is a form of energy that causes a change in temperature. Now, during chemical reactions, energy changes do occur. What that means is that either energy is absorbed or released. Now, we can be able to measure this change in energy, the energy released or absorbed. Why? Because the energy change results into a change in temperature. Endothermic and exothermic reactions. Now, we have seen that physical and chemical processes are often accompanied by either release of energy or absorption of energy. But one would wonder exactly where is the energy released from or absorbed into. Take note of two key terms in chemistry: system and environment. The system is the chemical or substance undergoing the change. The environment is what surrounds that chemical. It could be a solvent like water in case you are dissolving a substance, or it could be air in case you are burning that substance. Energy is released from the system into the environment or absorbed from the environment into the system. And the energy we are talking about is heat energy, which means the absorption or release of it is accompanied by change in temperature. But you see, you cannot measure the temperature of the system. However, we can measure the temperature of the environment. For example, in case you are dissolving a substance, you can be able to note the temperature change of the solvent. Now, bearing in mind that energy is neither created nor destroyed, it can only mean that the energy added into the environment is the same energy that is lost from the system. And equally, the energy lost from the environment will be the same amount of energy that will be added into the system. To understand this better, let us look at each of the two processes separately. And we are going to start with an endothermic process. An endothermic process is one that is accompanied by absorption of heat energy into the system. For example, in dissolving ammonium nitrate in water, the system, which is the salt, absorbs heat energy from the environment, that is water. So the temperature of the water will drop. Why? Because it has lost some of the heat energy into the system. But the energy of the system will increase because it has absorbed some energy from the environment. So if I can have an energy level diagram for the energy change in the system, you can imagine this point as the reactant. They possess this amount of energy. In converting to products, it gained some energy, and the energy of the product is higher than that of the reactant. So in the case of ammonium nitrate, solid ammonium nitrate has this amount of energy. When it is dissolved in water, It absorbs energy from the water, that is the environment, and the aqueous ammonium nitrate, which is the product, possesses a higher amount of energy. Now you can see the energy change. The amount of energy added into the system is shown by that, which is theoretically 25.8 kilojoules per mole. We shall come back to that later on. But what is important for you to notice in endothermic process is that the reactants possess lower amount of energy compared to the product. Now, on the other hand, an exothermic process is actually the exact opposite of an endothermic process. Now, it is a process that is accompanied by release of heat energy from the system. For instance, in dissolving sodium hydroxide in water, the system, sodium hydroxide, releases some heat energy into the environment, that is the water. So the temperature of the water will rise due to the added heat energy from the system. The energy of the system will thus decrease in the process due to the lost energy. Now graphically, you can think of this point as the reactants. They possess this amount of energy, and in converting to products, they lose some of that energy, and you can think of the product as being here possessing less amount of energy compared to the reactants. So like in the case of sodium hydroxide, the solid sodium hydroxide, which is the reactant in our case, possess this amount of energy at this level. Now in dissolving in water to form aqueous sodium hydroxide, it loses a certain amount of energy, usually 43 kilojoules per mole, and to form sodium hydroxide, the aqueous sodium hydroxide will possess less amount of energy. Now the energy change is calculated as the energy of products minus the energy of the reactant. So in an exothermic process, you realize the products possess less amount of energy compared to the reactant. So if we do calculate the energy change, then we shall have a negative. On the other hand, in an endothermic reaction, you realize the energy of the products was actually higher than that of the reactant. The energy change was a positive. Next, we look at something we call enthalpy, and we look at enthalpy notation. And enthalpy is the heat content of a chemical. It's denoted by a capital H. But you see, it is impossible to measure the heat content of a chemical experimentally. I said that earlier on. However, change in enthalpy or heat content can be quantified or measured in some way. How? Because it results in a change in temperature. For instance, when the energy was released in an exothermic reaction, it resulted to a rise in temperature of the water. Now, this is the result of the heat that is transferred from the chemical or the system to the water, and this energy is lost from the system. By noting the change in temperature, one can be able to calculate the amount of energy added to the water or drawn from the water, which will give us the energy change of the system. Change in energy is denoted by delta H, and it is calculated as delta H is equal to enthalpy of the product or energy of the product minus the energy of the reactant. In an endothermic reaction, the energy of the product is higher than that of the reactant. Why? Because energy is added into the system, and therefore the delta H is a positive. In an exothermic reaction, the process results into a loss of energy from the system, and therefore the energy of the product is less than that of the reactant, and therefore delta H is negative. For example, in the combustion of hydrogen to form water, the change in enthalpy is negative 592 kilojoules. It means 592 kilojoules of energy are lost from the system in the formation of water. Now, the next thing I want us to look at is bond breaking and bond formation. And to do this, I want to take you some few years back in Form 1, when we had this kind of a curve that we call the heating curve that we obtained when we heated a piece of ice and recorded the temperature at certain time intervals. And this is how we explained the nature of the curve, that when ice is heated, its temperature rises as the molecules absorb heat energy, and that is section AB. The heat energy absorbed is converted to kinetic energy, and as a result, the molecules vibrate even more vigorously. Eventually, the molecules gain enough kinetic energy to overcome the forces holding them together in solid. Now at this point, the molecules can change their position and the ice melts, and that is at point B. Now the temperature remains constant until all the ice has melted, that is section BC. The heat energy supplied during melting is used to overcome the forces of attraction holding the lattice together. It does not therefore result in temperature rise at all. The molecules have now greater freedom of movement in the liquid state. Now the amount of heat energy required to convert a given amount of a solid substance into a liquid at its melting point is called the latent heat of fusion. Latent means hidden, and the molar heat of fusion is the amount of energy required to convert 1 mole of a solid substance at its melting point into a liquid. Now the same amount of energy would be liberated in the reverse process when 1 mole of a liquid substance at its freezing point turns into a solid. Now we proceeded again and had the same heating curve, but this time for a liquid. And this is how we explained it. When a liquid is heated, its temperature rises as the molecules absorb heat energy. And the heat energy absorbed by the molecules is converted into kinetic energy, energy in motion. Now this causes the molecules to vibrate, and the vibratory motion of the molecules increase as more and more heating takes place. The temperature continues to rise steadily until the liquid starts to boil. Now at this point, the molecules have acquired enough kinetic energy to break away from each other completely. Now the temperature remains constant at the boiling point because the heat energy supplied is used to break up the forces of attraction between the molecules. The temperature does not change. Now the heat absorbed by a substance when changing from liquid into a gaseous state at constant temperature is known as the latent heat of vaporization. When molar quantities of substances are used, the heat absorbed by the particles as the substance changes from the liquid to the gaseous state at constant temperature is called the molar heat of vaporization. Now, the molar heat of fusion and that of vaporization of a substance can actually be used to estimate the strength of the intermolecular forces holding the particles together in the solid and the liquid states respectively. If the forces holding the particles together in the solid structure are strong, then the molar heat of fusion is actually high, and this is reflected in the high melting point of this substance. Now equally, when the forces holding the particles in the liquid are strong, the molar heat of vaporization is high, and this is reflected in the high boiling point of that substance. Now, throughout your studies in chemistry, you may have noticed that very few reactions proceed spontaneously. You see, most reactions require the application of some energy in order to start them. But again, once they start, they proceed without any further application of energy. For example, when methane is mixed with oxygen, it does not burn until a spark is applied. However, once it starts to burn, a large amount of heat is released. Heat is just one form of energy that is required by reactants to start a reaction. The other forms of energy may include light. For example, methane would react very slowly with chlorine in the dark, but in the presence of light, a violent reaction occurs. Now, methane is a molecular compound, and the carbon and the 4 hydrogen atoms in its molecules are held together by strong covalent bonds. Oxygen also exists as a diatomic molecule, and the atoms in its molecules are also held together by strong covalent bonds. You see, for a reaction to occur, the covalent bonds in both methane and oxygen must be broken first to obtain separate atoms. Now, energy is required to break these bonds, and therefore bond breaking is an endothermic process. Once the bonds have been broken, the atoms rearrange themselves and new bonds are formed in the products. Now, in the process of bond formation, energy is given out, and therefore bond formation is an exothermic process. The energy spent in breaking the bonds in the methane and oxygen molecules is less than the energy given out when the products are formed. So overall, the reaction therefore gives out energy, and these energy changes can be illustrated using energy level diagrams shown next. So if you think of this point as the reactant, then we shall have the methane molecule and the oxygen molecules as well. So you realize the carbon and hydrogen atoms in methane are held together by covalent bonds. Again, the oxygen molecules are held together by covalent bonds. Now, to start the reaction, we need to break these bonds. We set each of the atoms separately. So energy is put into the system in an endothermic reaction to have separate atoms. So there you have 1 carbon, 4 hydrogen and 4 oxygen atoms. Now, to convert that into product, again those atoms need to rearrange themselves. So again we have an exothermic reaction. In the combination of those atoms to form new bonds, energy is released, and therefore we have the product there, carbon 4 oxide and water. So if you look at that representation, you realize that the exothermic process is much more enormous than the endothermic process. So overall we have energy lost from the system, and therefore you realize the products will possess less energy compared to the reactant. But that is not the only energy that is available. You realize we had to put in some energy first to break the bonds. It's only that when the bonds were reformed in the rearrangement of those atoms, much more energy was given out than was put into that system initially. So if you look at that reaction, the chemical equation up there, you realize methane reacting with oxygen, that is a combustion of methane, to form carbon 4 oxide and water, the overall enthalpy change is a negative. Proceeding, calculating the enthalpy change. So we indicated that by measuring the temperature change, we can be able to calculate just how much energy is lost or gained by a system. The conversion is quite simple. Heat energy is equal to mass of the solution times specific heat capacity times the change in temperature. For example, when 4 grams of ammonium nitrate dissolves in 100 ml of water, there is a temperature drop of 2 degrees Celsius. Now calculate the enthalpy change. Now from that very basic point, you realize there is a drop of temperature of 2 degrees Celsius. Temperature of the water, which means 2 degrees Celsius have been absorbed into the system. So how much energy would be the equivalent of that? So from that formula we have there, let us first calculate the mass of the solution. And the mass of the solution is taken as the mass of the solvent, that is water in this case. So we have the volume of that water is 100 ml, which is equivalent to 100 centimeters cubed. Considering the density of water is 1 gram per centimeter cubed and density is given by mass over volume, then it follows that mass is equal to density times volume. The mass of 100 centimeter cubed of water is equal to 1 gram per centimeter cubed times 100 centimeters cubed, which will give me 100 grams, which is equivalent to 0.1 kilograms. The mass in that formula should be given in kilograms. Temperature change. Now it is important to note that the temperature is given on the Kelvin scale. But there is no difference. Why? Because a temperature change on the Celsius scale is equivalent to the same magnitude on the absolute temperature scale. A change of 5 degrees on the Celsius scale is equivalent to a change of 5 Kelvin on the absolute temperature scale. For example, if I have 20 degrees Celsius and that temperature drops to 15 degrees Celsius, the change in temperature is 5 degrees Celsius. Now, if you want to check whether it is the same on the absolute temperature scale, 20 degrees Celsius is equivalent to 293 Kelvin. 15 degrees Celsius is equivalent to 288 Kelvin. If you calculate the temperature change there, 293 to 288, again the temperature change is 5 Kelvin. The change is an absolute value. So we proceed. We have 4 grams of ammonium nitrate that is dissolved in 100 ml of water, the equivalent of 0.1 kilograms, and there is a temperature change of 2 Kelvin. That is what we have found from our calculations. Now I have mass 0.1 kilograms. The specific heat capacity that we use is that of water, and the specific heat capacity of water is usually 4.2 kilojoules per kilogram per Kelvin. The temperature change there is 2 Kelvin. So the energy absorbed is equal to 0.1 kilograms times 4.2 kilojoules per kilogram per Kelvin times 2 Kelvin, and that gives me 0.84 kilojoules. 0.84 kilojoules is the amount of energy that was absorbed into the system that resulted into a temperature drop of 2 Kelvin. Now 4 grams of ammonium nitrate absorbed 0.84 kilojoules of energy when dissolved in 100 grams of water. So I can calculate the number of moles that is equivalent to 4 grams of ammonium nitrate. The formula mass of ammonium nitrate is 80 grams per mole. So the number of moles is equal to mass over formula mass. 4 over 80 is equal to 0.05 moles. So again, I can rephrase my statement and say 0.05 moles absorbed 0.84 kilojoules of energy. So 1 mole will absorb how much? I can calculate that. So I have 1 times 0.84 over 0.05, and I get 16.8 kilojoules per mole. So 1 mole of ammonia when dissolved in 100 grams of water will absorb 16.8 kilojoules of energy. So that is what we call the molar heat of solution, and that is the enthalpy change that occurs when 1 mole of a substance is dissolved in a solvent to give an infinite dilute solution. So I can write that chemical equation there. We have ammonium nitrate dissolving in water to form aqueous ammonium nitrate, and there is an enthalpy change of plus 16.8 kilojoules per mole. Why is the change positive? Because energy is absorbed from the water and taken into the system, so the product has higher energy compared to the reactant. Now that kind of an equation is called a thermochemical equation, an equation that shows the enthalpy change in that process. So let me now try an exothermic process. And for example, when 5 grams of sodium hydroxide was dissolved in 100 ml of water again, the temperature rose from 22 degrees Celsius to 28. Calculate the molar enthalpy of solution of sodium hydroxide and write the thermochemical equation for the same. Now we have mass. Mass is equivalent to 0.1 kilograms. We have 100 ml of water, which is equivalent to 100 centimeters cubed. Given that the density of water is 1 gram per centimeter cubed, it means the mass of 100 centimeter cubes of water is 100 grams. Convert that to kilograms, again it is 0.1. Specific heat capacity. Specific heat capacity is equal to 4.2 kilojoules per kilogram per Kelvin. Temperature change is 28 minus 22, which gives us 6 Kelvin. So the formula there, delta H is equal to mc delta T. Mass times specific heat capacity times change in temperature. So that's 0.1 kilograms times 4.2 kilojoules per kilogram per Kelvin times 6 Kelvin, which gives us 2.52 kilojoules. So when 5 grams of sodium hydroxide dissolves in 100 grams of water, 2.52 kilojoules of energy are released, and that amount of energy causes a temperature change of 6 Kelvin. Now, to calculate the molar enthalpy of solution, I need to find out how many moles of sodium hydroxide is actually equivalent to 5 grams. So the formula mass for sodium hydroxide is 40 grams per mole. So the number of moles there is given by 5 over 40, which is equal to 0.125 moles. So again, I can say 0.125 moles of sodium hydroxide when dissolved in 0.1 kilograms of water liberated energy equivalent to 2.52 kilojoules. So what if I had 1 mole? So I calculate that as 1 times 2.52 over 0.125, and that gives us 20.16 kilojoules. So the molar enthalpy of solution of sodium hydroxide is 20.16 kilojoules per mole. The thermochemical equation is the same equation, only the enthalpy change. And remember, the energy was lost from the system into the environment, that is water, and that is why the temperature of water rose, which means the product in the system has less energy because it lost some of that energy to the environment, and therefore the enthalpy change is negative. The products possess less energy compared to the reactants. One thing I know you're wondering is, why is the mass of the solution taken to be the mass of water, and yet we are adding certain amount of a solid? Now, shouldn't the mass of the solution be taken as the sum of the mass of the water and that of the solid added? And the answer is no. You see, the contribution by mass of a solid dissolving into a solvent is negligible, and that is why we are calculating the mass of the solution to be the mass of water, and you must always do this. So do not worry about the added mass of the solid, thinking that it will contribute to the final mass of the solution. The final mass of the solution is the mass of the water. The contribution of the solid is negligible. Now, the next enthalpy of solution we calculate is the enthalpy of solution of sulfuric acid, concentrated sulfuric acid. And when 5 milliliters of sulfuric acid are added to 95 milliliters of distilled water, the temperature rose by 6 degrees Celsius. Now, given the specific density of sulfuric acid is 1.84 grams per centimeter cubed, calculate the molar enthalpy of solution of the acid. Now, the total volume of the solution is the volume of acid plus that of water. Now, in this case, you realize that two are liquids and therefore their volumes will add up. So we have 95 plus 5, which gives us 100 ml. The mass of that, we will take it as 100 grams. 100 grams, we use the density of water because the contribution and the change that may be introduced by the concentrated sulfuric acid, bearing in mind that its density is not the same as that of water, is negligible. So we will take as 100 ml of water, and that gives us 0.1 kilograms. Specific heat capacity, we always take that of water, that is 4.2 kilojoules per kilogram per Kelvin. Change in temperature is 6 Kelvin. Energy change is given by mc delta T, and that is 0.1 times 4.2 times 6, which gives us 2.52 kilojoules. So when 5 ml of conc sulfuric acid is added to 95 ml of water, energy in the equivalent of 2.52 kilojoules is released. Now we need to calculate the number of moles of the acid. So the mass of the acid will be given by density times volume. The density of the acid is 1.84, multiplied by the volume is 5 centimeters cubed, which gives us 9.2 grams. Calculating the number of moles, we have mass over formula mass. So we have 9.2 grams over 98 grams per mole. So we have 0.1 moles. So 5 ml of conc sulfuric acid is equivalent to 0.1 moles. So from our calculation, we had 0.1 moles would liberate 2.52 kilojoules of energy. How about 1 mole? So that will be 1 mole times 2.52 kilojoules over 0.1, which gives us 25.2 kilojoules. 1 mole of the acid will liberate 25.2 kilojoules. So the molar enthalpy of solution of sulfuric acid is minus 25.2 kilojoules per mole. So again, you realize the enthalpy change there is negative. Why? Because energy is released from the system. If we write the thermochemical equation there, we have the liquid sulfuric acid plus water gives us the aqueous sulfuric acid with an enthalpy change of negative 25.2 kilojoules per mole. The next type of enthalpy is the enthalpy of combustion, and I'm going to look at the enthalpy of combustion of ethanol. Ethanol is a fuel. Now, how do I measure the enthalpy of combustion of ethanol? Do I put the thermometer on the flame as ethanol burns? No. Now, when ethanol burns, I can use that flame to heat a given amount of water. Now, the temperature rise that will occur as a result of heating the water is what should give me the amount of energy that is liberated during the heating or the combustion of ethanol. How? Because the assumption is all the amount of heat energy released during the combustion will be used to heat the water. So the heat liberated in the combustion of ethanol is equal to the heat transferred to the water. But there is an assumption, and we shall see the consequences of that. But let's first work out an example. When 0.46 grams of ethanol was burnt and the flame used to heat 200 ml of water, the temperature of the water rose by 15 degrees Celsius. Now calculate the molar enthalpy of combustion of ethanol. Now the mass, we shall use the mass of the water. The heat is transferred to the solution, that is water. So the mass is 0.2 kilograms. Why? Because 200 ml is equivalent to 200 centimeters cubed. Given the density of water is 1 gram per centimeter cubed, the mass is 200 grams, which is equivalent to 0.2 kilograms. Specific heat capacity fixed 4.2 kilojoules per kilogram per Kelvin. Temperature change is 15 Kelvin. Enthalpy change is mc delta T, 0.2 times 4.2 times 15, which gives us 12.6 kilojoules. So when 0.46 grams of ethanol was burnt, it liberated 12.6 kilojoules of energy. How do you get this energy? This is the energy that is transferred to water. So number of moles is given by 0.46 grams over 46 grams per mole, which gives us 0.01 moles. So I can be able to rephrase that and say 0.01 moles of ethanol when burnt in oxygen liberates an amount of energy equivalent to 12.6 kilojoules. Now, how much would 1 mole of ethanol give? By doing that, I will calculate the molar enthalpy of combustion of ethanol. So 1 mole times 12.6 kilojoules over 0.01 moles. So that gives us 1260 kilojoules. So the molar enthalpy is 1260 kilojoules per mole, a negative. Why? Because the reaction, the combustion of ethanol, is an exothermic reaction. It liberates energy. So the thermochemical equation there is ethanol plus oxygen, giving us carbon, oxide and water, with an enthalpy change of minus 1260 kilojoules per mole. And we define the molar enthalpy of combustion as the enthalpy change that occurs when 1 mole of a substance is completely burnt in oxygen. So when 1 mole of ethanol is completely burnt in oxygen, it liberates 1260 kilojoules of energy. The assumption in this experiment is that all the energy liberated in the combustion of ethanol is transferred to water. But this is usually not the case. You see, some of the energy is lost to the surrounding, while some is absorbed by the apparatus. So experimentally determined heats of combustion are usually lower than the expected theoretical values because of the heat gained by the apparatus and that lost to the surrounding, which is not accounted for in the calculations. Next is heat of neutralization, and neutralization is a reaction that occurs between an acid and a base. For example, hydrochloric acid would react with sodium hydroxide to form a salt called sodium chloride and water. The ionic equation for that reaction is hydrogen ions reacting with hydroxyl ions to give water. Now, during a neutralization reaction, energy is released. So you know what I've just told you, that a neutralization reaction is usually an exothermic reaction. Let's take an example. When 50 ml of 1 molar hydrochloric acid was added to 50 ml of 1 molar sodium hydroxide, both at 20 degrees Celsius, the highest temperature recorded was 30 degrees Celsius. calculate the molar enthalpy of neutralization of hydrochloric acid by sodium hydroxide. During that experiment, the temperature is recorded with time as the acid is being added to the base or vice versa, so that we know the highest temperature that is attained. So in our case we had 30, but initially both the acid and the base were at 20 degrees Celsius. So in our calculations, total volume is 100 mils, 50 ml of acid plus 50 ml of the base. Mass will take the mass of water, the product is water, and 100 ml of water would make 0.1 kilograms. By now you must have seen that. Specific heat capacity is 4.2 kilojoules per kilogram per Kelvin. Temperature change is 10 Kelvin. So delta H is equal to 0.1 times 4.2 times 10, which gives us 4.2 kilojoules. So when 50 ml of 1 molar HCl was neutralized by 50 ml of 1 molar sodium hydroxide, the reaction liberated 4.2 kilojoules of energy. So we want to calculate the molar enthalpy of neutralization of that acid, so we find the moles of the hydrogen ions. We had 50 ml of 1 molar hydrochloric acid, so we calculate how many moles are there. So we have 1 times 50 over 1,000, and we find 0.05 moles of the acid was used, or 0.05 moles of the hydrogen ions. Now from the ionic equation you realize the mole ratio is 1 to 1. The mole ratio of hydrogen ions and hydroxyl ions is 1 to 1. So it can only mean that 0.05 moles of the hydrogen ions would react with 0.05 moles of the hydroxyl ions. And again the ratio between them and water is 1, which means again 0.05 moles of water is liberated. So we say the moles of water that are formed is 0.05. So the molar enthalpy there, we calculate it, we have 1 mole times 4.2, because if 0.05 moles generate 4.2 kilojoules of energy, how much will 1 mole liberate? So we have 1 times 4.2 over 0.05, and we find 84 kilojoules per mole, and it has to be a negative. Why? Because the reaction was exothermic. So the thermochemical equation, hydrogen ions react with hydroxyl ions to give water with an enthalpy change of minus 84 kilojoules per mole. Consequently, we define the enthalpy of neutralization or heat of neutralization as the enthalpy change that occurs when 1 mole of hydrogen ions in an acid are completely neutralized by an alkali. Now, most strong acids and bases reactions release about 57 kilojoules of energy in a neutralization reaction to form 1 mole of water. But if one of them is a weak acid or base, the molar enthalpy of neutralization is lower. For example, if I have a strong acid like hydrochloric acid and I react with a weak base like ammonium hydroxide, the enthalpy of neutralization realized there is negative 51.4 kilojoules per mole, which is less than the 57 one. Again, if I have the acid being the weak one, like ethanoic acid reacting with a strong base sodium hydroxide, which is a strong base, would have an enthalpy change that is again lower than the 57. Now when both the acid and the base are weak, the enthalpy is even smaller. For example, ethanoic acid reacting with ammonium hydroxide, both are weak. Ethanoic acid is a weak acid and ammonium hydroxide is a weak base. So you realize the enthalpy of neutralization there is negative 50.4 kilojoules per mole. That is very important. You need to notice that if one of the reacting species in a neutralization reaction is a weak acid or a weak base, then the enthalpy of neutralization is lower than the theoretical one, which is usually around 57.2 kilojoules of energy. Next is heat of displacement. But before we do that calculation, let's demonstrate something briefly. Now on the screen I have a blue solution of copper 2 sulfate. Copper 2 sulfate salt dissolved in water. and again I have some ion fillings. Now when I add the ion fillings into the copper 2 sulfate solution, look what happens. Now with time you realize that the solution turns light green and there is a deposit of a red brown solid at the bottom there. So you know what is happening is that ion is displacing copper 2 ions from the solution of copper 2 sulfate. Remember, copper 2 ions are usually blue in color and they are the ones that give the solution that blue color. On the other hand, copper metal is red-brown in color. So what has happened here is that the ion has gone into the solution and has displaced the copper 2 ions. The copper 2 ions are deposited as copper solid, while the ion goes into the solution to form iron 2 sulfate. Now the iron 2 ions are light green in color, and that is why the color of the solution has changed. Now that is a classic kind of a displacement reaction. Ion has displaced copper 2 ions from their solution. Now usually this kind of a reaction is accompanied by energy changes. When ion displaces copper 2 ions from the solution of copper 2 sulfate, energy changes do occur. So we have to calculate that enthalpy change. So let's take an example. When excess ion was added to 100 ml solution of 0.5 molar copper 2 sulfate, a red-brown solid was deposited and the solution turned light green with a temperature rise of 25 degrees Celsius. Calculate the molar enthalpy of displacement of copper ions. Mass of the solution, we have 100 milliliters of the solution. Now remember, it is copper 2 sulfate that is dissolved in water, and we have said the solid that dissolves in water contributes negligible mass to the total mass of the solution. So the total mass of the solution is still the total mass of the water. The increment in mass due to addition of copper 2 sulfate is negligible. Specific heat capacity C is 4.2 kilojoules per kilogram per Kelvin. Again, we use that of water. Temperature change 25 Kelvin. Our formula, delta H is equal to mc delta T. 0.1 times 4.2 times 25 gives us 10.5 kilojoules. When excess ion is added to that solution of copper 2 sulfate, there is an enthalpy change of 10.5 kilojoules of energy. Now you realize the ion was in excess, and why was that so? So that all the copper ions will be displaced from the solution. From the ionic equation up there, you realize the mole ratios is 1:1. So if we have excess ion being added, it means all the copper in the solution will be displaced. As a matter of fact, some ion will remain unreacted. So next we calculate the moles of copper that are present in that solution. We have a 0.5 molar solution of copper 2 sulfate. So if 0.5 moles are in 1000 ml, how about in 100 ml of that solution? We calculate how many moles are there. So we have 0.5 moles times 100 ml over 1000, which gives us 0.05 moles. And those are the moles of copper 2 sulfate, which are the same moles of copper 2 ions. Next, we calculate the molar enthalpy. If displacement of 0.05 moles of copper 2 ions liberated 10.5 kilojoules of energy, how much would 1 mole of the same copper 2 ions liberate? So we calculate 1 mole times 10.5 kilojoules over 0.05 moles, and we get 210 kilojoules. But because it is the molar enthalpy, it is 210 kilojoules per mole. So the thermochemical equation is there that ion displaces copper 2 ions to form iron 2 ions plus copper solid with an enthalpy change of minus 210 kilojoules per mole. That is the molar enthalpy of displacement of copper 2 ions by the ion. So we define the heat of displacement as the enthalpy change that occurs when 1 mole of a substance is displaced from a solution of its own ions. Standard conditions for measuring enthalpy changes. Various experiments have shown that the enthalpy changes are affected by physical states of the reactants, temperature, pressure, and concentration. Now, in order to compare enthalpy changes for different processes, some standard conditions have been. The standard conditions of temperature and pressure adopted for reactions are 25 degrees Celsius, that is 298 Kelvin, and 1 atmosphere of pressure, which is equivalent to 101.325 kilopascal, respectively. Values of enthalpy changes that are measured at these conditions are called standard enthalpy changes. Standard enthalpy changes are given the special symbol delta H standard. Now, that symbol is used to mean the standard, and it implies a pressure of 101.325 kilopascal or 1 atmosphere and a temperature of 298 Kelvin. A subscript is also added to the symbol to indicate the type of enthalpy change involved. For example, if we have delta H standard, F is the standard enthalpy of formation. We could also have the standard enthalpy of combustion. We have a subscript C there, and then we also have the standard enthalpy change for hydration. It's indicated there. For example, when hydrogen is combusted in air, we have hydrogen plus oxygen, and the standard enthalpy of formation of water there is negative 296 kilojoules per mole. Next, we look at energy cycle diagrams and the Hess law. The enthalpy change for some reactions cannot be determined experimentally because the reactions cannot take place under normal conditions. For example, consider methane. Methane is a molecule made up of carbon and hydrogen. But it is not possible to determine the enthalpy of formation of methane in an ordinary lab. Why? Because it is not possible to synthesize methane from carbon and hydrogen. Now, where direct synthesis of a compound is not possible, we have an alternative route, and that is to determine the enthalpy of formation theoretically using other measurable enthalpies. Now, one method of doing this involves measuring the enthalpy of combustion of the compound. For example, we can measure the enthalpy of combustion of methane because we can burn it in air in a lab. And then there is also the enthalpies of combustion of its constituent elements. We can burn carbon and measure the enthalpy of combustion. We can also burn hydrogen and measure the enthalpy of combustion of that. Now, these values are then linked in an energy cycle diagram with the enthalpy change of formation of the compound, and that is what we want to look at. So if I start there with a carbon reacting with hydrogen to give me methane, and then I'll have the enthalpy of formation of methane, and that is what I'm saying is not possible to measure in a lab. But then I can measure the energy of combustion of methane. I can burn methane in air and I will get carbon dioxide and water. So there I have the standard enthalpy of combustion of methane. The next thing I can also be able to do is burn carbon. If I burn carbon, I will form carbon dioxide, and again the enthalpy of combustion there, I can be able to measure it. The other thing I can also do is that I can burn hydrogen. If I burn hydrogen, I will form water. Remember, I'm burning them in air, so it's hydrogen plus oxygen, and the enthalpy of combustion of hydrogen there will give me water. So I call that the red route and the black route. You realize whether I first form the methane and burn it, I end with carbon dioxide and water. And again, if I burn carbon and then burn hydrogen, again I get the same product. Now, what I have on the screen is what we call an energy cycle diagram. You start with the same reactant and you end with the same product, irrespective of the route you take, whether the red route or the black route. Now, the interesting thing is that the enthalpy of combustion of carbon plus the enthalpy of combustion of hydrogen should give us the enthalpy of formation of methane plus the enthalpy of combustion of the same methane. That means the black route should be equal to the red route. Now, that is very interesting, but we link those values in that energy cycle diagram, and believe me, from that you can be able to theoretically calculate the enthalpy of formation of methane. That cannot be determined experimentally, but by linking those enthalpies in that energy cycle diagram, where we start with the same reactant and end with the same product irrespective of the path we take, you will calculate the enthalpy of formation of methane. And that is governed by the Hess law, of constant heat summation. And it states that the enthalpy change in converting reactants to product is the same regardless of the route by which the chemical change occurs. So the reactant there is carbon and hydrogen, the product is carbon dioxide and water. So whether we burn carbon and hydrogen or we first form methane and then burn methane, the route doesn't matter. The enthalpy change in converting reactants to product is the same irrespective of the route by which the chemical change occurs. Now let's take an example so that you understand better. Given the following, draw an energy cycle diagram and calculate the enthalpy of formation of carbon 2 oxide. Now what that means is that you cannot be able to form carbon 2 oxide in a normal laboratory setup. So we calculate it theoretically using the energy cycle diagram. So we've been given that the enthalpy of combustion of carbon there in the first equation is negative 393 kilojoules per mole. We also have the enthalpy of combustion of carbon monoxide, which is equal to negative 283 kilojoules per mole. So if we link the two, we can be able to calculate the enthalpy of formation. So I start with the equation for the formation of carbon 2 oxide. Carbon plus oxygen to give me carbon 2 oxide. That is the enthalpy of formation I cannot be able to calculate. But then I have the enthalpy of combustion of that. So if I burn carbon 2 oxide, I get carbon 4 oxide. And the enthalpy there I was given as negative 283 kilojoules per mole. On the other hand, I can burn carbon. I have been given that when I burn carbon, the enthalpy of combustion of that is negative 393 kilojoules per mole. Now the red route should be equal to the black route. So you know what that means? Delta H, the enthalpy of formation of carbon 2 oxide, plus minus 283 kilojoules per mole, that is the enthalpy of combustion of that carbon 2 oxide, should give me the enthalpy of combustion of carbon. The reactants are carbon and the product is carbon 2 oxide. So irrespective of the route, the enthalpy change is the same. So if you do that, delta H will be negative 110 kilojoules per mole. I hope you can be able to see that. I've used different colors so that you can be able to conceptualize that. Whether you take the red route or the black route, that should give you the same enthalpy change. Let us calculate the enthalpy of formation of ethanol. Now given the following, draw an energy cycle diagram and calculate the enthalpy of formation of ethanol. Now ethanol is a compound of carbon, hydrogen and oxygen, but you cannot be able to combine the three atoms in a lab to come up with the molecule. So what we normally do is that we calculate the enthalpy of combustion of that ethanol and the enthalpies of combustion of the constituent elements to link them in an energy cycle diagram, and we'll be able to theoretically calculate the enthalpy of formation of ethanol. But careful, you do not burn oxygen because oxygen does not react with oxygen. In combustion, we react elements with oxygen. So I start the first equation there, of course, is the equation for the formation. Always start with that. So we have carbon plus hydrogen plus oxygen should give us ethanol. That is the enthalpy of formation, which we cannot be able to determine experimentally. But I can burn ethanol. And when I do that, I will have carbon 4 oxide plus water. Now you have to have a balanced equation there. The other thing I can do is that I can burn carbon. If I burn carbon, look at the balancing there of oxygen, we will have again carbon 4 oxide. Make sure you balance your equations. Again, I can burn hydrogen. If I burn the 3 hydrogen molecules, if I combine with 3/2 oxygen molecules, I'll get the 3 water molecules. The same product we got when we burned ethanol. So again, the red route should be equal to the black route. That is the enthalpy of formation of ethanol plus the enthalpy of combustion of that ethanol should give us the enthalpy of combustion of carbon plus the enthalpy of combustion of hydrogen. Now look at this. The enthalpies in the equations are given as kilojoules per mole. but you realize when I'm burning carbon, I have 2 moles of carbon. So it can only mean that I will multiply that figure by 2. On the other hand, I have 3 moles of hydrogen gas. The value that was given on the equation is negative 296 kilojoules per mole. So 1 mole is the one that liberates that amount of energy. So if I have 3 moles of that, I will liberate 3 times that amount of energy. So we have there delta H plus minus 1368, the enthalpy of combustion of ethanol. The enthalpy of combustion there is not multiplied by any number because we were burning 1 mole of ethanol. So is equal to 2 times the enthalpy of combustion of carbon. There we have 2 molecules of carbon plus 3 times negative 296, the enthalpy of combustion of hydrogen. So if I do that, you will end up with negative 276 kilojoules per mole. The enthalpy of combustion of the enthalpy of formation of ethanol is negative 276 kilojoules per mole, which means it is an exothermic process. Still having that in mind, let us look at the relationship between the heat of solution, the heat of hydration, and lattice energy. Now, in the beginning, it was found that dissolving substances in water can be accompanied by absorption or evolution of heat. Now, when an ionic compound is formed from its constituent gaseous ions, energy is given out, and this energy is known as lattice energy. Lattice energy is defined as the energy change when 1 mole of an ionic compound is formed from its constituent ions in gaseous state. Now that's very important. Look at that equation there. We have sodium ions reacting with chloride ions to form sodium chloride. Now if you look at the status symbols, they are indicating the ions are in gaseous state. So when we formed that, we said energy is liberated. So the enthalpy there is negative 781 kilojoules per mole. That is the lattice energy that is released when that ionic compound is formed from its constituent ions in gaseous state. Now, dissolving an ionic solid involves first the interaction of water molecules with the ions in the solid to such an extent that the solid dissociates into monoatomic gaseous ions which scatter in all directions in the water. Therefore, energy equivalent to lattice energy is usually absorbed, and this is the opposite of the process through which the ionic solid was formed. For example, when we have now sodium chloride dissolving, it will first dissociate into gaseous ions, sodium ions and chloride ions, and you realize the enthalpy change is the reverse of the one that we had there. We just changed the sign because now in this case the same amount of energy is now absorbed into the system. Secondly, the ions get attracted to the polar water molecules and become hydrated. That means they are surrounded by water molecules. So we have the sodium ions plus the water to get sodium ions now in aqueous state, from the gaseous to the aqueous state. And again we have energy liberated there equivalent to 390 kilojoules per mole. And again we have chloride ions in gaseous state. They are hydrated to give chloride ions now aqueous, and therefore again we have energy change there. An amount of energy equivalent to 384 kilojoules per mole are liberated. Hydration involves formation of new bonds between water molecules and the ions. The process is exothermic. Hydration energy is released. Now, energy change when 1 mole of gaseous ions become hydrated is what is the hydration energy. Hydration energy is the energy change when 1 mole of gaseous ions become hydrated. The overall enthalpy change of solution now depends on whether the endothermic or exothermic process is larger. For sodium chloride, the endothermic process is greater than the exothermic process, and therefore the enthalpy of solution of sodium chloride is a positive value. Now the following energy cycle diagram can be used to calculate the heat of solution of sodium chloride. So if you look at that energy cycle diagram, the red route is what we have described. The solid sodium chloride First of all, the lattice breaks to form sodium and chloride ions in gaseous state. That is what we call lattice energy. And then the gaseous ions get hydrated into sodium and chloride ions in aqueous state, and there we have the enthalpy or standard enthalpy of hydration of those ions. Now on the black route there we have direct from sodium chloride, the solid, to the aqueous state of the ions, sodium and chloride ions. Now the heat of solution is equal to lattice energy plus hydration energy. The black route is equal to the red route. For example, given the following, calculate the heat of solution of sodium chloride. So we've been given their sodium chloride forming the gaseous ions. There we have the enthalpy as plus 781 kilojoules per mole. Again, the hydration there of sodium ions. There we have the hydration energy is negative 390, and we also have the hydration energy for chloride ions as negative 384. Now if you link those values on that energy cycle diagram, just replace those figures on the energy cycle diagram and use that formula, you will be able to calculate them. So let's do that. Lattice energy there plus 781 kilojoules per mole. Hydration energy is the sum of the two because we have the hydration of sodium ion and hydration of chloride ion. Negative 390 plus negative 384, and that should give us, the sum of that should give us the enthalpy of solution. So heat of solution is equal to plus 781 the lattice energy plus minus 390 plus minus 384. That gives us plus 7 kilojoules per mole. So the overall process is endothermic. We had said that earlier. I can actually represent that information on an energy level diagram. That energy cycle diagram can be transformed into an energy level diagram. So if I start with the sodium chloride solid there, the first thing I need is to break the bond. I need lattice energy to be put into that, so because it is the reverse of lattice energy. So I give it a plus 781 kilojoules per mole. And what I end up with there is the gaseous ions, sodium and chloride. Now again I need that to form the aqueous ions, so I need the enthalpy of hydration, the sum of the enthalpy of hydration of sodium and that of chloride, so it gives me minus 774 kilojoules per mole. So finally I end up with sodium and chloride ions in aqueous state. So we have the initial and the final part of that process. So the difference between the two is the overall change. So that is the heat of solution. So if I do that, you realize I will end up with plus 7 kilojoules per mole. That is the overall enthalpy change, and that is the enthalpy of solution. Now during hydration, the amount of energy released depends on the size of ions and the charge that those ions carry. Now the enthalpy of hydration of various ions is usually given, and you need not to memorize them. You will always be given in an examination. Now the hydration energy is usually multiplied by the number of moles of the individual ions being hydrated. Where there are more than one, for example in magnesium chloride, there are 2 chloride ions. So you will have to multiply the enthalpy of hydration by 2. Finally, having spoken of energy, let us look at fuels. And a fuel is a substance that produces useful energy when it undergoes a chemical or a nuclear change. Now, energy produced in such reactions can either be used directly as heat, or it can be converted into other forms of energy, for example, electrical energy. Now, fuels can be solid, such as nuclear fuel, coke, coal, charcoal, wood, and others. Others are liquid, for example, petrol, kerosene, and diesel oil. Or they can even be gases like natural gas, biogas, water gas, and liquid petroleum gas, which is usually called LPG. Now, heats of combustion of fuels are especially important because they provide one way of comparing the heat energy produced when equal quantities of different fuels are burnt. Now, generally, not all the heat energy liberated by a combustion process is utilized. For example, when coal burns in a power station, only 50% of the heat energy liberated is converted into electrical energy. Now, the other 50% is converted into other forms of energy, and much of the energy goes to waste, and that determines the efficiency of a process. Heating values of fuels, and the heating values of fuels has the units of kilojoules per gram. It is obtained by dividing the molar enthalpy of combustion by the formula mass of the fuel. For example, ethanol has an enthalpy of combustion of negative 1360 kilojoules per mole. If we divide this by the formula mass of ethanol, which is 46, we get the heating value of ethanol as 30 kilojoules per gram. Now, the heating value of a fuel is therefore the amount of energy given out when a unit mass or a unit volume of fuel, in case the fuel is a gas, is completely burnt in oxygen. Again, the heating values of different fuels are given. So when you are choosing a fuel, you will have to consider various aspects. For example, that heating value. You need to choose a fuel that has high heating values. You also need to consider the ease and rate of combustion, availability of that fuel, the ease of transportation, storage, environmental effects, and of course the cost of that fuel.
Humans have long been fascinated with what exactly it is that makes up the world we live in. Today we know that atoms are the fundamental building blocks of matter, but this was not always the case. It took humankind many thousands of years to accept atomic theory as an explanation of how the elements in nature fit together. Almost 2,500 years ago, the Greek philosophers Leucippus and his student Democritus first proposed that objects were made up of many indivisible particles of various shapes and sizes that they called atoma, from the Greek word for uncuttable. Around 360 BC, Plato gave mathematical shapes to the four roots or basic elements: earth, fire, air, and water that the Greeks believed made up all the universe. And in 350 BC, Aristotle added a fifth element that he called quintessence. He thought that this was the element of the heavens. However, he rejected the theory of atomism put forward by Democritus. After the fall of the Greek and Roman empires, scientific thinking was suddenly seen as magic, causing science in Europe to stagnate throughout much of the Dark and Middle Ages. It would take a full 1,600 years before scientists like René Descartes and Sir Isaac Newton would once again put forward the theory of a universe made up of small particles or atoms hooked or glued together.